idea of this net growth momentum optimization, or what we just call the net growth accelerated gradient, okay, abbreviated as NAG, to measure the gradient of the cost function not at the local pursuit, but slightly ahead in the direction of the momentum. So if let's just look at the formula, okay? This formula and the previous one in momentum. Look at here, and then here. Almost identical, right? Almost identical. The only difference is where you apply this where you obtain this gradient, this gradient, where you obtain this gradient, first order derivative. Okay, in the next row, you obtain the first order gradient, okay, at theta plus beta times n. So it try to go, it doesn't get the gradient from the theta place. It get the gradient from theta plus beta n. Okay, so it gets the gradient a little bit further to where it should, it is predicted. So why do we need to do that? Think about this. If after all, okay, this is a vector, okay, this is a vector. Keep in mind, this is a vector, okay? Even though I tell you this is a first order derivative, but they are like micro terms here, okay? If you just imagine they are like three terms, then you can imagine this is a three-dimensional space, because that's easier for you to understand. I do not mean this is that's only like three dimensions. No. Yeah, many dimensions. But imagine we have only three dimensions. Help you to better understand, better visualize this. Okay. So this one. Okay. If imagine it's a three dimension. That it's pretty much a function. You are going to get a vector, right? It's going to be a vector, just like n is a vector. We call this a momentum vector, right? Okay, this one is a vector too. Okay, the first one is like we do a partial derivative of j over the first variable, right? The second one, let's assume that it's x, y, z. Okay, so the first term is we do a partial derivative over x. The second one we do a partial derivative over y. The third one we do a partial derivative over z. Okay? So we get like a vector, right? We get a vector. Okay? So let's look at here. Think about this. If you try to get a vector, okay, that pretty much is like if you are doing that, you have to try to calculate that gradient vector here. The direction you get is this direction, right? Right? Okay, it's this direction, right? But if you try to get a direction here, okay, the gradient, okay, it's going to point to here, right? Right? The vector is going to point to here, right? Let me ask you this. Where is the optimum place in this figure? Huh? Everybody can tell? It's written here, right? Optimum, right? Right? It's here, right? Can someone tell me this direction is going to bring you closer to this point, or this direction is going to bring you close to this point? This one, right? This one, right? Because, well, you are trying to reach the minimum, okay? So the closer you get to this optimum, okay, the more likely this direction is going to pointing to this optimum, right? Right? Okay, so the next row, okay, find this, observe this, and then he say like, okay, we shouldn't just apply theta here. We apply theta plus beta n here, okay, because plus beta n, it means we are getting closer to the optimum. Okay, so when you try to get this gradient, okay, then this gradient is going to pointing toward the optimum more accurate. Okay, more accurate as compared to the vanilla momentum optimizer. Okay, so that is the concept. That is the concept of Nesterov accelerated gradient. Okay, and well, so this is really a small tweak. Okay, but it works very well. Okay. In general, momentum vector will be pointing in the right direction, okay? So it will be slightly more accurate to use the gradient measured a bit further in that direction, rather than using a gradient at the original position, okay? So, okay, as you can see, the natural update ends up slightly closer to the optimum, okay? Just slightly better. But after a while, this small improvement add up, and the NAG end up being significantly faster than the regular momentum optimization. Okay, because it's better for every iteration. Okay, it's better than momentum for every iteration. So this small improvement will add up. It will make the NAG a much better choice than the momentum optimization. Okay? And also, know that when the momentum pushes the weight across the value, okay, let me just still use this one, okay. So remember, when you are close to a bottom, okay, because you have speed, right? And now you are trying to calculate the derivative, the gradient. It is still positive here, right? So, well, you still increase the speed a little bit. Okay, so it's going to roll past this momentum, right? Previously, I told you momentum optimization is going to move past here and then come back, past here and come back, right? 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 But the NAG, when it reaches here, okay, what happens that it's going to use the next position to calculate the gradient, right? So the place it used to calculate gradient is most likely going to be here. So it's going to point toward the opposite direction. Okay? So which will cancel out its current speed. Okay? So not only the friction will reduce its speed, also this part, this reverse gradient is going to cancel the speed here as well. So it's going to stabilize. It's going to make a stabilization faster than the momentum optimization as well. Okay? So there are two advantages of this NAG optimizer. Okay? Okay. So this is the code for the technical code for the NAG optimization. Again, it's very simple. Well, you can tell it's very similar to momentum optimization. So you just the code is still, you are still using the momentum optimizer. Okay, the only difference is that, okay, here, okay, you still have your beta value, okay, so the momentum hyperparameter is still there, okay. You only need to add one additional parameter, use next row, set it to be true. Then you are going to use the next row gradient, you know, accelerated gradient, okay, not the momentum, okay. So that's it, okay. So, any question? Okay, no question. Let's take 10 minutes break. We'll come back. We'll continue the discussion of the next optimizer, which is called end up grade. Okay.